Let's go over a full example on how to graph a rational function using calculus concepts. So my very first step is I want to try to find the intercept, so either the x or y intercept. In this case, I will try to find my x-intercept because for an x-intercept, you just set the x values to 0. So if I set all the x values to 0, I get 2 times 0 divided by 0 plus 1, and that means my y value is also going to be 0. So it turns out that my x and y intercept is at the point 0, 0. Okay, after that, I want to go ahead and find my critical points. And my critical points will allow me to use the first derivative test where I can find the max and min points. Okay, in order to find the critical points, we need to take the derivative of this rational function. So since we're dividing here, we need to use the quotient rule. So the derivative of 2x is going to be 2. And then we multiply by the denominator, and the denominator here is going to be x squared plus 1. And then the quotient rule states that we need to subtract. And now I can subtract the numerator, which is 2x, and then I can multiply by the derivative of the denominator, and the derivative of x squared plus 1 is going to be 2x. Okay, after that, we would then divide our whole expression by the denominator squared. So since our denominator is x squared plus 1, if we want to square that, we would put that in brackets x squared plus 1 and raise it to the power of 2. Okay, so there is the expression for my first derivative, and then after that, let's go ahead and see if we can simplify this. So we have y prime equals. Okay, so if I distribute that, I get 2x squared plus 2. And then if I distribute this negative sign onto all of that, basically we have 2x times 2x, which is 4x squared. And since there's a minus sign, it will be minus 4x squared. And then we still have the denominator as being just x squared plus 1 all to the power 2. Okay, so now we need to simplify the numerator here. So 2x squared minus 4x squared, and then we have this positive 2, right? So I'm going to rearrange this as putting the positive 2 in front. And then if I combine those terms, 2 minus 4 is going to be negative 2x squared, and then all divided by x squared plus 1 all to the power 2, and this is y prime equals. Okay, so we're looking pretty good in terms of simplifying our first derivative here. And for our first derivative, we want to set this equal to 0, right? So if we want to set this equal to 0, in order to find the critical points, we just need to focus on the numerator here, right? It doesn't matter what the denominator is, especially when you have a fraction. So when a fraction equals to 0, that happens when the numerator equals to 0. So if I go ahead and factor out the 2 on the numerator, I get a 1 minus x squared, and then I can set that equal to 0. Okay, so basically what we're doing is we're just taking our numerator there, we're factoring out the common factor there, and then we're setting that equal to 0. And when we set that equal to 0 here, it turns out that we just need to solve this quadratic here. So x squared minus 1 equals to 0. That means x equals to plus or minus 1. Okay, so what we need to do next is these are our critical points, right? So now we need to determine whether those critical points represent maxes or mins. So what we need to do now is we can draw a horizontal number line here. All right, and that's my first derivative test. So I will be using my first derivative test, and from here we can just put a negative 1 and a positive 1 on the number line here. And this number line represents the first derivative, so we can just write like y prime over here on the side. Okay, so now when we're using the first derivative test, it looks like we have 3 regions for this graph. So we want to pick regions, we want to pick numbers in the regions there. So over here on the far left hand side, a very safe number that I can pick is maybe 100. Okay, and if I plug in 100 into that x variable there, that's going to be 2 minus a very big number, so this whole section here is going to be negative. Okay. One more thing that you want to note is the denominator here is always going to be positive, so you don't need to put any numbers into the denominator there. Now a number in the middle here, in the yellow region, it could be 0. So if I plug in 0 over here, 2 minus 0 is going to be 0. So 2 minus 0 is going to be a positive expression. So the middle term here is going to be positive. And then finally, we can just pick a number at the far end here, like negative 100. If I plug in negative 100 over there, negative 100 squared will be positive. So it'll be 2 minus a very big number. And that will mean that this will be a negative region there. Okay, so based on that, it turns out that the slope is going, it's decreasing there, then increasing, increasing there, then decreasing. So it turns out we have a minimum here and a maximum at 1. Okay, so what we're going to do next is I'm going to go back to the beginning here, and let's just go ahead and, you know, I'll just erase this for now, and let's go ahead and since we found our critical points to be, 1 and negative 1. Those are our critical points. Let's just find out what the actual coordinates are. So let's evaluate f of 1 and f of negative 1. So if I plug in 1 and back into my original function, I get 2 divided by 2, which equals to 1. Okay, so it turns out that my critical point 1 comma 1, 1 comma 1 gives me my max, right? So that's my max. And if I plug in negative 1, I get negative 1 on the numerator, but I get a positive 1 on the denominator, so that gives me negative 1. So my other critical point, which is x value of negative 1, has a y value of negative 1 as well. This will be my minimum. Okay, so I have a maximum at 1 comma 1 and a minimum at negative 1 comma negative 1. Okay, so now that we're done with our critical points, let's go ahead and find our inflection points, and our inflection points happen at our second derivative, right? So going back to here now, let's go ahead and see if we can find our second derivative here. Let me just erase this, and I will work my second derivative from over here now. So it's very important that you get your first derivative correct, and we're going to be using the quotient rule one more time. So oops, that should be a plus here. Okay, so the quotient rule states that we need to take the derivative of the numerator there. So the derivative of the numerator there is going to be bracket negative 4x. And then I multiply it by the denominator, and the denominator is going to be x squared plus 1 all to the power 2. And then the quotient rule states that there's a minus sign, and then I'm going to multiply by the numerator, which is 2 minus 2x squared. And then erase all this, and then I multiply by the derivative of the denominator here. So the derivative of this expression right there. Let's see if we can get all that. We've got to be careful here because we need to use the chain rule here, but we have a 2 there, so that 2 gets soccer kicked to the front. So 2 bracket x squared plus 1, and then we multiply by the chain rule here, which is going to be 2x. Okay. Right, so that is the numerator right there, and then we divide by, the quotient rule states that we divide by the denominator to the power 2. So if I square that, I get 2 times 2, which is power of 4. Okay, so this is looking pretty ugly right now, and we have to be very good with how we simplify things. And one thing that I do notice here is that there's an x squared plus 1 and an x squared plus 1 there. So that is my GCF. So what we're going to do now is we're going to factor out that GCF. So we're going to factor out the x squared plus 1. And this is where you have to be very, very careful here with your brackets. If I factor out a binomial there, I'll put a big square bracket. And what I have next in the brackets will be negative 4x. And then this 2 now becomes a 1, right? Because I factored out one of the x squared plus 1 terms. So this will now be x squared plus 1. And then what we'll do next is, I guess there's a 2 here in blue, sorry, a 2 in green. There's a 2x and a negative sign. If I multiply all 3 of those terms there, if I multiply the negative sign, the 2, and the 2x, if I multiply all that out, we get negative 4x. 4x, and then we also have this 2 minus 2x squared term hanging around. Okay, so let me just kind of use my green marker there. That negative 4x is the result of multiplying all the expressions in green. So a negative sign times 2 times 2x gives me my negative 4x, and then we still have that 2 minus we still have this term just hanging around there. Okay, so that's a very important skill right there to be able to factor out that that GCF, which is a binomial right here. And then we still need to divide by the denominator all raised to the power of 4. Okay. Okay, let's see if we can continue to simplify this. One thing that you might notice here is there's an x squared plus 1 and there's an x squared plus 1 there. So we can cancel that off, and that will now become a 3. And then we can also just start distributing the numerator there. So if I multiply this out, I get negative 4x cubed minus 4x. Okay, and then if I distribute this into the brackets, I get negative 8x plus 8x cubed. And that is all going to be divided by our new expression on the denominator, which is x squared plus 1 all to the power 3, and this is my second derivative. Okay, so I'm being very careful with all my algebra steps because it's super, you can definitely make a mistake pretty quickly here, so I'll do my best to go through this very slowly here. So if I subtract those, 8 minus 4 is going to be 4x cubed, and the negative 4x minus 8x is going to be negative 12x. And that is all going to be divided by the denominator all to the power of 3. Okay, now this is my second derivative, and if I want to set my second derivative equal to 0 to find my critical points, we're only focused on the numerator again, right? So just like the previous step here on the first derivative test, when we set our fraction equal to 0, we only care about the numerator. And if I factor out the common factor here, which is 4x, bracket onto x squared minus 3, we can set that equal to 0. It turns out that this expression gives me a value of 0, and this expression right here gives me x equals to plus or minus root 3. So those are the x values that make the second derivative equal to 0. And after that, I can draw a horizontal number line here, and this is my second derivative. And we're going to put these x values, 0 and plus or minus root 3, on the number line. So there's a 0, there's a root 3, and here's a negative root 3. And this is pretty tough because now we have 4 regions to test. So let's go ahead and just test this region over here, the tail ends. We can do that very quickly. Let me kind of erase this, and let me just kind of write this as 4x. Bracket x squared minus 3, and let's just see if we can test the regions there. So a very safe number in this region is going to be positive 100. So if I plug in positive 100 into all the x expressions here, the denominator is always going to be positive. The 4x here will be positive, right? 4 times 100 is positive. And if I plug in a positive here, 100 squared minus 3, that's also going to be a positive, right? So this whole region is going to be positive. Okay. Now, if I take a number in the tail end here, like negative 100, and if I plug that in, negative 100 in here will be positive. Positive plus 1, all to the power 3 will be positive. If I plug in negative 100 over there, I get a negative expression there. And I think I just missed the squared here, so they're squared there. And if I plug in negative 100 here, that'll be positive. So positive minus 3 will be positive. And if I calculate all that out, a negative and a positive, that means my tail end here, it turns out my tail end here is going to be negative. So this will be negative over here. And probably in the middle regions here, probably the safest numbers that you probably want to pick are going to be positive 1 and negative 1. And if you go ahead and just plug those numbers in, I'll just do it quickly here. This will be positive and this will be negative, so just make sure you verify that. But that's how your concavity works for this particular problem. So it turns out that we have an inflection point at negative root 3, we have an inflection point at x equals to 0, and we also have an inflection point at positive root 3 because we're changing signs at those values, right? Okay, let's go back to the original part of the problem here, and let's go ahead and if we can evaluate f of root 3. and f of negative root 3. Okay, so if I plug in root 3 for all the x's here, it turns out we get 2 root 3 on the numerator. And on the bottom, we get root 3 squared, which is 3, plus 1, which is 2 root 3 over 4, which is root 3 over 2. Okay, so what that means is we have an inflection point at root 3, comma, root 3 over 2. And if I go ahead and just plug in f of negative root 3, just by symmetry, I can tell that we get negative 2 root 3 on the numerator, and on the denominator we get positive 4. So our inflection point will be at negative root 3, comma, negative root 3 divided by 2. So those are our inflection points by symmetry. Okay, so I think that's most of the major calculations for this particular problem. The last thing that we need to do here now is that we need to graph this. Okay, so I've gone ahead and I've kind of constructed my xy axes here. I have my first derivative test up here, f prime of x, there in red, and I have my concavity levels down here for f double prime of x. And I've also just kind of found all my key coordinates here. So 0, 0 is an inflection point and one of my xy intercepts. I have a maximum at 1, 1 and a minimum at negative 1, negative 1. And I have my inflection points that I just calculated here. So if I go ahead and try to construct my graph here, if you want, you can kind of put these maximum symbols over here at positive 1 and at negative 1 we can put this minimum shape there. And if I had to sketch this, so this is the point 1, 1, and this is the point negative 1, negative 1. And if I had to use some simple logic here, it looks like the graphs are just going to probably go through the intercept here and just connect over there, right? And if I had to use some logic here, it's probably going to go through that point and this point over here. And I think the graph is probably going to concave like that a bit, and probably like this. Oops, not that great. Curving out like that. Okay, and this point right here is root 3, comma, root 3 over 2. And this point over here is going to be negative root 3, comma, negative root 3 over 2. And this point right here is 0, 0. Okay, so that's a rough sketch of my graph here. Now let's go ahead and check that everything is lining up correctly here. So on my first derivative test, if I take a look at this blue region right here to the left of negative 1, so here's negative 1. If I look at the left-hand region here, is this slope negative? And the answer is yes, that's definitely a negative slope. Let's take a look at this middle region here in green. So from negative 1 all the way to positive 1, do I have a positive slope there? And the answer is yes. And then from the right-hand side of 1, is the slope going to be negative? And the answer is yes. So my first derivative test lines up quite well. All right, so let me just erase this. Okay, now let's take a look at my concavity here. So over here on the left-hand side, on the left of negative root 3, is it concave down? Is this concave down right there? And the answer is yes, because when we're looking at concavity, this means concave down, and we're just taking this part of the graph right there, right? So there's my concavity graph there, and this part right here is concave down right there. Okay, that looks good. And let's take a look at this region right here. From negative root 3 to 0, is that concave up? So this green region right here, clearly this is concave up, right? It's like a parabola opening up, so that looks good. And then over here, I'm concave down from 0 to root 3, and from 0 to root 3. All the way over here, this is definitely concave down. That's a parabola that's opening down. And then finally over here, I have concave up. And does this represent concave up at the tail end there? And the answer is yes, because remember, concave up means this, right? This is the general shape of concave up. And I'm just taking the left-hand side of that parabola right there, right? So this kind of matches with that. Okay, so that verifies this problem here. So we've gone through all the major steps, and yeah, one of these rational functions here, if you had to sketch this graph using calculus concepts, it takes quite a bit of work, and it might take a full page or two to write up a proper solution. But here's a nice little guide to kind of help you with these kind of problems.